In this session, we will be discussing about Hall effect transducer. This Hall effect transducers are widely used for the measurement of displacement and for the measurement of magnetic and electric field intensities and such similar applications. Here the material used will be a semiconductor material, either a p-type or n-type. Some typical examples are indium arsenide phosphide and doped silicon. Moving on to the working of Hall effect transducer, we will be explaining the working of the transducer with the help of a construction diagram, and the material used for the explanation will be a p-doped semiconductor. So we can even understand the working with the help of n-type material, but for the time being we will be considering a p-type material. So now consider the diagram where the semiconductor material is acted upon by an external electric field as well as magnetic field. The magnetic field is applied in the Z direction, so the magnetic field intensity is Bz, and there is a electric potential difference applied in the X direction, so that will constitute a current Ix in the X direction. Since this is p-doped material, the majority carriers will be holes. That means holes will be traveling in the X direction, say from the left to right. When a electric current, when a charge carrier moves in a magnetic field, there will be a force acting on it which will be perpendicular to both the direction of movement as well as the direction of application of magnetic field. So because of this reason, because of this Faraday's law, there will be a force acting on the holes which is perpendicular to X direction as well as Z direction. So that is a force in the Y direction. Here in this case, the direction will be upwards, since BZ is towards into the surface, and Ix in the X direction, the force acting on it will be upwards. This results in an accumulation of holes on the top of the semiconducting material. And if the Z or direction of current travel anything reverses, there will be of course a corresponding alternation in the accumulation of holes. But in this case, for this particular example, the holes will be accumulated on the top side, which will result in a corresponding potential gradient from top to bottom. From top to bottom there will be a potential gradient that can be measured, and this particular voltage is called Hall voltage. This Hall voltage is used as a sensing element for many applications like electric field intensity measurement, magnetic field intensity measurement, or even some derived application like displacement transducer. We will be seeing that in the upcoming session. Now just going through the working. As a p-doped, here a p-doped semiconductor subjected to a magnetic field Bz in the Z direction and an electric field Ex in the X direction. A current Ix flows in the X direction, so the holes move in X direction across magnetic field and experience an upward magnetic force due to the Faraday's laws, which results in accumulation of holes on the top surface and electrons on the bottom surface. An electric field Ey, known as Hall field, is set up as a consequence. So this is briefing on the working. And now now since we know there is no current flow in Y direction, in the X direction there is current flow due to the external voltage difference applied, but there is a Hall voltage generated in the Y direction, but since there is no a closed loop, there won't be any current flow. Since there is no current flow, a force equilibrium has to be maintained. Every charge carrier should be acted upon by equal amount of force in the y direction, so that we can obtain an equilibrium equation with the help of the magnetic the force due to magnetic field and force due to electric field. So the equation, from the equation we can derive expression for the Hall voltage VH equal to RH into Ix Bz divided by H, where RH is a Hall coefficient. It is negative for n type and positive for p type. H is the dimension. Here in this case the height or width of the material. Bz is a magnetic field intensity. Ix is the current. So this equation will be the governing equation in the case of a Hall effect transducer. So moving on to a Hall effect displacement transducer. Here in this case the same principle which we studied just before is used for the measurement of displacement. How this Hall effect transducer is used for measuring displacement. Here the arrangement is shown in the bottom. You can see the HET, that means Hall effect transducer, in a fixed position. So the HET is fixed, but there are two sets of magnets, magnet 1 and magnet 2, and it is connected to a arm which is capable of movement. So the magnet 1 and magnet 2 are capable of moving with the reference as HET. So when magnet 1 comes closer to HET, there will be the voltage, Hall voltage will be increasing. Similarly, when magnet 2 come close to HET, there will be a corresponding decrement in the Hall voltage. So this change in voltage or direction of change voltage difference will be directly related with the displacement. So this can be used as a transducer for measuring displacement, and the voltage, Hall voltage, will be proportional to the displacement. HET being used to measure a small displacement. If the displacement brings magnet 1 close to the transducer, the output will be increasingly positive, and it will be increasingly negative if magnet 2 moves closer to HET. So this is how Hall effect transducer is used as a displacement transducer.